Following on from the previous session where we looked at the vector equation of a line, today we're going to look at the intersection point of two vectors, how we can figure out if two vectors do intersect or not, and then we're actually going to have a look at some real-world applications of this. So if we are given the vector equations of two different lines, we can investigate which of three scenarios will occur. So imagine we are working in 3 dimensions, in which case it is possible that the two vectors could intersect, and if that's the case, then the value of the variables is consistent in all three equations. It's possible that they could be parallel and hence never intersect, in which case the direction vectors will be scalar multiples of each other, or as you can see from this graphic here, it is possible that the two vectors could be skewed. So that's to say that they are not parallel and they will never intersect. And if that's the case, then the values are not consistent. Now, to have a look at what we mean by this, we'll have a look at an example. Here we have the vector equations for two lines R1 and R2, and we're asked to show that the lines intersect and to find the coordinates of the point of intersection. So, in this instance, we know, or we're looking to show, that they do actually intersect. So if they do intersect, we can work on the rationale that there will be a point such that the x coordinates for this line and the x coordinates of this line will be shared, and that's going to be the same for y and z. So if there is an intersection, there will be one point in 3 dimensions which is found on both lines. So from that starting point then, we need to generate an expression for x from both lines. So from the first line, we can say that the x coordinate will be 3 plus s, the y coordinate will be s, and the z coordinate will be negative 1 plus s, just remembering that we multiply each value in the direction vector by the component here, s. So we've done that for R1, we'll also do it now for R2, and we end up with these values. Now, as we said, if they do actually intersect, there will be a point at which the x coordinates are the same, the y coordinates are the same, and the z coordinates are the same. So what we can do then is take the x values and set them equal to each other. So if we say the first, or the x value, or expression for x from the first equation must be, if they intersect, the same as the value for x from the second equation. And we can also do the same then for the y coordinates and the z coordinates, and we end up with these three expressions here. From equation 1, we can solve that s equals 3, and we can then substitute s equals 3 into equation 2, and we end up with a value of t, which equals 2 1/4. And then finally, substituting s equals 3 into equation 3, we also end up with a value of t equals 1/4. So we can say that these values here are consistent. And it's that consistency we're looking for to show that the two lines do intersect. We can also check by substituting s equals 3 into R1, and then actually generate the values, because the question also asks us to find the coordinates of the intersection. So if we substitute s equals 3 into R1 for the component here, we can see that the actual coordinate of x will be 3 plus 3 times 1, which is 6, and y and z will take these values as well. So the coordinates, therefore, of the intersection are going to be 6, 3, and 2. We're going to have a look at an application of vectors and indeed the intersection of lines with this question here. So we are given the position vector of a boat A t hours after it leaves a harbour, and that's t 30/15, and a second boat B is passing near the harbour, and its position vector is given at at time t by r2 equals 55 plus t and 10, 10. The question then, how far apart are the two boats at the time the first boat leaves the harbour? How fast is each boat travelling? And are the boats in danger of colliding if one of the boats does not change course? So it should be fairly axiomatic here that this part C is relating directly to what we just looked at, albeit in this question we're only looking at 2 dimensions. So if you feel that you can tackle these by yourself, have a go at that, otherwise just follow the solutions 3. So how far apart are the 2 boats at the time the first boat leaves the harbour? Well, when the first boat leaves harbour, we can establish that time is going to be 0. So therefore, boat A will be have a position of 0, because this will be 0. So 0 times 13, 0, 15 is going to give us this. The position for boat B, obviously, again, T will be 0, so this will be 0. But the position, therefore, will just be this position vector here, 50 and 5. So how far apart are the 2? Well, that's just going to be using the equation for the distance between 2 lines. So 50 minus 0 squared plus 5 minus 0 squared. Add them together, take the square root, and you're going to end up with an answer of 50.2 kilometers. Part B, how fast is each boat traveling? Well, when you've got a vector, we said that this component is to do with the, this is the position vector, and it's the second part here, which is the direction vector. So we're interested in the direction vector because in this context, that is going to tell us the speed. So how fast is each boat traveling? We, in essence, need to find the magnitude of the direction vector, and that will give us the velocity. So for boat A with a direction vector 13, 15, we can find the magnitude, which gives us 33.5 kilometers, and for boat B, using the same process, we can find that the magnitude of the velocity, is 14.1 kilometers. Part C then is what we're interested in, especially are the boats in danger of colliding if one of the boats does not change course. So exactly as we did in the previous question with 3 dimensions, we are going to have a look at what happens if we set the x coordinates or x components equal, and if they're consistent, we can interpret that the boats will collide, and if they're not, they won't collide. So if we take the individual x components to start with, then so the x component for R1 would be t times 30. The x component for R2 is going to be 50 plus 10t. And we can have a look at what happens when we solve that. So that would give us 20t equals 50, so we can solve to get a value of t is equal to 2.5 hours. We're then going to do the same for the y components, and we're going to again solve this equation here for t, which is going to give us 15t minus 10t equals 5, so therefore t is equal to 1 hour. Given that the value of t is not consistent here, we can conclude that the boats will not collide.